This is lesson 2-3. We're going to be multiplying special cases. So the essential question is, what patterns are there in the product of the square of a binomial and the product of the sum and the difference? So squaring a binomial turns into what we'll call a perfect square trinomial. And so we want to kind of look at why is a plus b squared considered a special case when we're multiplying. So visually we can see that when we multiply a plus b squared, that means we're taking and multiplying a plus b times itself. Okay, so if something's being squared, I'm multiplying it times itself. So I'm not just squaring both of the terms, I'm actually distributing each term. So if I distribute a times a is going to give me a squared, and then a times b is going to give me a times b. So I have a squared plus ab, and then b times a is still ab, because we write them alphabetically. And then when I multiply b times b, I get plus b squared. So from this distribution, I can see that this simplifies to a squared plus I have two ab terms and a b squared. So visually, if this is a plus b, this would represent ab, right? So see how we have two of them. This would be a b squared, and this would be an a squared. And so this pattern of if I have a binomial squared, that's always equal to the square of the first number plus double the product of the two numbers plus the square of the second number. And so we're going to use this pattern rather than multiplying out to look at some expansions. So we're going to use this a plus b squared equals a squared plus 2ab plus b squared. And so what I'm going to do with this is I'm going to take and write out our pattern. So our pattern is that a plus b squared is equal to a squared plus 2 times a times b plus b squared. So we're using essentially this formula every single time. So for this first problem, 5x is the a. So we're going to do 5x squared is equal to 2 times 5x times -3 plus -3 squared. So when I plug in to that pattern, I have to then simplify to find the result. So 5x squared is actually 25x squared. When I wrote this, it was just 5x, but I put an extra square there, so there shouldn't be that extra square. It was just the 5x squared from the pattern. So I wrote this one correctly. I wrote a regular 5x. I didn't add that extra square on accident. So 2 times 5 is 10. So right now I have 10x times -3 is -30x. And then -3 squared is +9. Okay, so what we see from here is that 5x minus 3 squared is equal to 25x squared minus 30x plus 9. So what this comes in handy for is when I have squares of numbers that I don't necessarily know. So 29 squared, if I had a calculator, this would be really easy. But if I don't have a calculator, a perfect square trinomial or a square of a binomial makes this a lot easier. So what I want to think about this is, instead of as 29 squared, is I can think of this as 30 minus 1 squared. And so if we look at the pattern, So we've got our a squared plus 2 times a times b plus b squared. And in this case, our a is 30. So those first two blanks are a's, the second two blanks are b. B is -1. And so we'll see that this is pretty easy to do in our heads versus maybe multiplying out 29, having to do that by hand. So 30 squared is 30 times 30, so 900. And then 2 times 30 is 60, times -1 is -60. And then 1 squared, -1 squared is 1. Okay, so this gives us 900 minus 60 plus 1. And so 900 minus 60 is 640. So this is 641. Okay, so that was really easy numerically, squaring 30 and squaring 1 and multiplying some numbers together, as opposed to if I didn't have a calculator. Okay, so this might help us also when we're finding the area of a rectangle by squaring a binomial. So in that last example, it was easy to do subtraction because I had a 30 and a 1. If I do something -1 here, it won't necessarily be an easy number. So what I want to think about this is, if I use it as addition, the area of this would be 36 squared. So instead of thinking about it as 36 squared, I can think about it as 30 plus 6 squared. And then I can use my pattern of a squared plus 2 times a times b plus b squared. Okay, so looking at this, 30 is my a. And this time, positive 6 is my b. And so if I simplify this, 30 squared is 900. And then 2 times 30 is 60, times 6 is 360. And then 6 squared is 36. So if I add these together, 900 plus 360 is 1260, and then 1260 plus 36 is 1296. And since we're talking about area, remember that this is in square units, since they didn't give us a unit of measure. Okay, so 36 times 36 is 1,296. And again, the pattern just makes it a little bit easier to do in your head when you don't have a calculator. For the last example for part 1, E, we're looking at the area of the shaded region. So we have 2 sides labeled on each rectangle, and they're measured the same. So that means that these are both squares. And so I can think about these 4 triangles that I'm trying to find the area of as a large square. So it's this outside square. So the area of this would be this whole region. And then minus the area of the smaller square that's on its side. So notice that one has a side of x. So I can subtract that, the area of that square. And so what I want to think about to create my equation is the area of this is going to be x plus 4 squared minus x squared. Right? So because the sides of the large square on the outside is x plus 4, and then the sides on the small square on the inside is x. So the area of the large square is x plus 4 squared, so that whole highlighted region. And then if I take away the white part, with an area of x squared, that'll give me the area of everything. So since I have x plus 4 squared, I want to use my pattern to expand that. So I have a squared plus 2 times a times b plus b squared minus the x squared that represents the smaller square. And so within this x plus 4 squared, our a term is x. So we're going to have x squared plus 2x. And then our second term, our b term, is 4. And so times 4 plus 4 squared is going to be the rest of the pattern. Remember that we still have that minus x squared from us removing the unshaded region. And so if I square this and simplify, I've got x squared plus 2 times x times 4, so that's plus 8x. And then plus 4 squared is 16 minus x squared. And so the area of the shaded region is represented by this expression. Notice that we have like terms. So we have an x squared and then a minus x squared. So that means that the area is just 8x plus 16. And again, we're talking about area. So we want to represent this with square units. So that is a perfect square trinomial created using the square of a binomial. So again, this model is that I have this perfect square, and so using the tiles, the pattern shows up as a squared plus 2ab plus b squared. And we used it to kind of simplify some perfect squares in the situation that maybe we don't have a calculator. The second half of this lesson is on difference of two squares. And so difference of two squares is represented here by the product of a plus b times a minus b. And so using the distributive property, let's see what happens. So if I distribute a times a is a squared, and then a times b, negative b, is minus ab. So remember that we write those alphabetically. Then if I distribute the b times a is a b, because I want to write it alphabetically. And then b times negative b is minus b squared. And so what happens here is we actually have like terms that cancel. So with the perfect square, the like terms combined. In this one, I have a negative AB plus a positive AB. And so this ends up just being a squared minus b squared. Okay, so if I have a plus b times a minus b, I end up with just a squared minus b squared. And so these types of binomials, so I have a sum and a difference that are the same, these are called conjugates. That creates what we call a difference of two squares. So it's two perfect squares, a squared and b squared, and we're subtracting them. So this difference of two squares title is referring to what the answer looks like. Okay, so when I'm given the problem, I have a sum times a difference. Okay, and notice that it's the same value. So this is the sum of two numbers times the difference of the same two numbers. Those pairs are what we call conjugates. So the conjugate of a binomial is the sum and the difference of those same two terms. So for this one, I have 6x plus 1. So the conjugate is going to be 6x minus 1. Okay, so when I can recognize that it's the same two numbers or terms, one's a sum, one's a difference. So 3x minus 4, its conjugate would be 3x plus 4. For the last one, 3 minus 8y, the conjugate would be 3 plus 8y. So notice that it's not necessarily that the sign in front of the constant changes. It's that sign in the middle. So this turned into a minus. So I have to have one of each in order for it to be conjugates. And so what's special about conjugates is that idea that everything cancels in the middle when I combine like terms. Okay, so they're the same terms, but the sign's opposite in the middle. So one's a sum times a difference. And that those two pairs are what we call conjugates. So these problems end up to be a little bit faster because of that, it's that much shorter pattern. So the pattern for a sum times a difference is that it's a difference of two perfect squares. Okay? And so notice that the first term for both of these is 5x. So the first term in our answer is going to be 5x squared. The second term for both of these are 7. So the second square is going to be 7 squared. And so recall that 5x squared is 5x times 5x. So that's going to be 25x squared. And then 7 squared is 49. So it's going to be 25x squared minus 49. For the answer of our difference of two squares. So this can also be helpful when I'm multiplying numbers together if those numbers are an equal distance from a different number. Okay, so what I'm looking at here is that I can think about 43 as 40 plus 3. And I can think about 37 as 40 minus 3. So I now have conjugates. I have the sum of 40 plus 3 and the difference of 40 minus 3. And so that allows us to do the difference of two squares instead of multiplying 43 times 37. So the first term for both of these is 40. So my first number that I'm squaring is 40. And then the last term for both of these is 3. So that means I'm subtracting 3 squared. So then if I simplify these, 40 squared is 1,600. Minus 3 squared is 9. So if I subtract 9 from 1,600, that gives me 1,591. So that makes that multiplication a little bit easier, again, if I don't have a calculator. So 43 times 37, I can express that as 40 plus 3, and its conjugate, 40 minus 3. So I can use that idea to find the area of the rectangle using the difference of two squares here. So I have a rectangle who has a side length of 25 and another side length of 15. So if I think about that as I want it to be the sum of two numbers times the difference of the same two numbers. And so I can use 20 and 5 for that. So I can think about 25 as 20 plus 5. And I can think about 15 as 20 minus 5. Okay, so again, the area of this we know is, and I didn't write that down, is 25 times 15. And so to simplify this process, I can think about it as 20 plus 5 times 20 minus 5, because then I know it's just going to be the difference of those two numbers squared. So if I square 20, and I square 5, and I subtract those two numbers, that's going to give me my result. So 20 squared is 400. 5 squared is 25, and so that means that the area of this rectangle is 400 minus 25, or 375 units squared. So for today's assignment, you are to be using these patterns to expand functions. So you will get this printed out so that it doesn't have to be displayed all of class. Know that the sub will collect this assignment from you today so that I can see how much work you got done, and then I will return it to you tomorrow. So you should be doing this on separate notebook paper, writing your name on it, titling it with page 67 and all those numbers, and then turning it in at the end of class.